When we look up at the night sky, we see stars, hundreds, thousands if you're lucky, depending on where you are, but what we don't see are the planets, those invisible travelers orbiting distant suns. For most of human history, we didn't even know they were even out there. Were we alone? Was Earth rare? Or were we just one rock in a cosmic gravel pit of life-friendly worlds? And then came Kepler.
You have reached the signal. This is the Archive, a safe space for the curious, science and technology-minded.
Thanks for tuning into the Archive. I'm Steve, your friendly neighborhood science and tech enthusiast. And if you're into that sort of thing, make sure you click subscribe. And check out my other science and tech videos and help me spread the knowledge. Now, in 2009, NASA launched one of the most game-changing scientific missions of our time, the Kepler Space Telescope. It was a $600 million spacecraft with one job: to find planets. And more specifically, it was looking for Earth-like planets around sun-like stars in orbits where water could exist. Sounds like a simple task, right? But what Kepler found was not just a few planets and not just dozens of planets, it found thousands of planets. And suddenly, everything we thought we knew about the universe changed overnight. So what was Kepler? Great question. Kepler was basically a giant digital camera in space, a 0.95 meter telescope designed to stare at a single patch of the sky, not sweeping across the stars and not scanning the galaxies, just one fixed view deep into the constellations Cygnus and Lyra. And for nearly 4 years, Kepler focused on a sliver of the sky. But in that tiny slice, it observed over 150,000 stars, watching for the slightest dips in brightness. Just these tiny flickers that happen when a planet crosses into the front of a star. So this method is called the transit method. It's like noticing a gnat flying across a car's headlight from 1,000 miles away. And it's absurdly precise. And Kepler was built to notice those unnoticeable flickers. Now, Kepler isn't magic. Kepler didn't send back glossy images of alien Earths. It measured light curves. So charts of a star's brightness over time, and if that brightness dipped at regular intervals, then boom, you have a planet. Well, maybe. See, a dip in light doesn't always mean a planet. It could be a binary star system, a sunspot, even instrument noise. So Kepler flagged KOIs, Kepler Objects of Interest. That needed follow-up. To confirm these planets, scientists used ground telescopes with radio velocity tools, transit timing variations. They were watching for gravitational tugs between planets, and in some cases, statistical modeling to estimate confidence levels. But was Kepler perfect? Not quite. About half of all gas giant candidates turned out to be false positives. Even some Earth-sized ones turned out to be straight noise or misreadings. But over time, with better data and a clever verification system, Kepler's confidence rate for small rocky planets hit around 90%. And by the time it signed off in 2018, Kepler had discovered 2,781 confirmed exoplanets. It identified nearly 5,000 additional candidates and suggested that billions more likely exist throughout the Milky Way. So let me say that again. Kepler gave us evidence that planets are not rare. They're actually pretty common, and in fact, the average star likely has at least one. So before Kepler, we thought solar systems like ours might be rare. But after Kepler, we realized the universe is a planetary playground. And among those thousands, dozens were roughly Earth-sized. A few even orbit in the habitable zone, the sweet spot where water could exist. So planets like Kepler 186f, which we'll talk about in a little bit, became headline and homework for astrophysics students everywhere. I know one of the big questions that typically come up is, can we visit them? So let's bring it back to reality for just a second, because most of Kepler's planets are hundreds or thousands of light years away. I mean, Kepler 186f, which we'll talk about later, is 580 light years. And I mean, that's trillions of miles from Earth. And even with today's technology, it would take us tens of thousands of years just to get there. So no, we're not booking any space flights just yet. But that, in a sense, wasn't Kepler's job to begin with. It wasn't supposed to find where we were going. It was meant to show us what's out there. And boy, did it do that. So with the help of Kepler, I wanted to look at some of the most weird planets that Kepler has found so far, even one that could be Earth-like. So let's dive into the weird, the wild, and the wonderful, starting with a planet that's like the real-life Tatooine. For those that know, you know. So starting with the first planet on the list, it's called Kepler 16b. I call it the Tatooine planet, and so do a lot of other people apparently. So for you Star Troopers out there, buckle up because we're heading to the OG Star Wars crossover, Kepler 16b, the real-life Tatooine. And if you've ever wondered what a double sunset might actually look like in real life, yo, it's right here. Now, picture stepping outside on this gas giant. And yeah, unfortunately, it's mostly gas. No breathable atmosphere, so sorry, you can't land on it. But in the sky, not one sunrise, but two sunrises. A big orange K star and a smaller red dwarf sweeping down on the horizon in a perfectly staged interstellar ballet. Instagram's going to explode if you were able to get a picture of this. Maybe with some hashtags like sunset goals or jealous aliens everywhere could be the theme of that, right? Now, here's where it gets real. Before Kepler 16b, models suggested circumbinary planets were rare and any planet forming that close to two stars would be booted into deep space or shredded with tidal forces. I mean, scientists believed that they had to orbit far, far out, like beyond 7 times the binary star distance. But Kepler 16b is practically cheek to cheek with its star. It's only 0.43 astronomical units away. Just to give you an idea of what that is, Venus is at 0.72 and riding in a resonant orbital sweet spot, which keeps it in a surprisingly stable dance ring, carefully avoiding gravitational death. So found safe inside this cell is sandwiched between basically chaotic teeth of instability. But believe it or not, this skinny stability corridor that it sits in is why it actually exists. But I think one of the questions that you're going to ask is, how did it get there? So latest hydrodynamic simulations tell us the planet likely formed farther out, beyond the dusty, chaotic binary region, and then migrated inward through the protoplanetary disk, like a cosmic surfer chasing a wave, slowing as it hit the pressure pileup zone carved by the binary star. And also check this, Kepler 16b is one of the best measured exoplanets ever. So why, you ask? Great question. It transits crazy time variations. Each time it passes across one star, the binary motion drifts by minutes. Scientists used a combo of transient timing, duration variations, and even radial velocity from ground space telescopes like SOFI from France to nail its mass at 0.31 Jupiter masses. So in short, this planet is so well mapped, its diameter is known to be within 0.3%. It's ridiculous. Kepler 16b is basically the micrometer of exoplanet precision. I think it's because there's a lot of Star Wars nerds that are working at the science place that does all this. Okay, to wrap up Kepler 16b, or Tatooine, it has double sunsets. It does a great job of walking an orbital tightrope. It does planet migration from a masterpiece perspective, showing we can build and park gas giants in wild places. And just from a speculative standpoint, it could be a moon habitat, giving life cuddlers a little bit of hope if the planet was warmer. And data geeks delight, the precision is fit for a NASA swag, basically. So Kepler 16b turned theory on its head. It's proof that nature doesn't follow or have assumptions like we do. It does what she wants, and that's why we love her. All right, so brace yourself, cosmic thrill riders. I didn't write that, that just came up. But this next stop is not for the faint of hearted. We're diving into the blazing, scorched metal cores of what may be the hottest planet ever discovered in the universe. I think, maybe, I might be over-exaggerating that point, but I'm talking about Kepler 70b and Kepler 70c. They're dubbed the Hell planets, living reminders that sometimes planets survive by being eaten by stars, then emerge as fiery ghosts. So these planets are really less planets and more cosmic embers. They're leftovers from a star-eating ordeal, if you will. Just imagine two gas giants that are orbiting a star that expands into a red giant. They get swallowed, losing their fluffy hydrogen layers, burned nearly to nothing, and left only as a scorched iron core. Now, today, those cores, Kepler 70b and Kepler 70c, are now circling a sub-dwarf B star at a breathtaking speed. I'm talking 5.76 and 8.23 hours per orbit. Now, the other crazy thing about it too is that it has reached temperatures over 7,000 K hotter than the surface of our sun and rivaling lava from a supernova. So it's really a literal hellscape that glows like a miniature stellar ember. So plot twist, are they real? Data from Kepler spotted brightness reflections, not transits, so scientists flagged them as candidates. But later studies suggest that these signals might instead be stellar pulsations, essentially vibrations in the star itself, not orbiting cores. It's still up in the air, and they might be a survivor of stars eating planets or mere illusions or artifacts of a star's pulse. But assuming they do exist, here's the science that makes them so dramatic. Let's talk about sub-dwarf B stars. These are post-red giant. They shed most of their hydrogen and are shrinking down after their violent expansion. Those cores survived inside the star, spiraled inward due to atmospheric drag, then got ejected back into orbit as the star contracted. So their current orbits are fantastically tight. I'm talking like 0.006 astronomical units, nearly grazing the host star. So generating surface gravity changes and tidal stress beyond imagination. Now, here is some head-spinning physics. Tidal dragging and orbital decay. Now, given their proximity, tides likely raised bulges inside the cores, turning orbital energy into heat. Without an atmosphere, that heat just melts rocks. It's like a cosmic slow torch. And we're talking about mass loss at 7,000 K. Any remaining volatiles would be vaporized instantly. These cores likely atrophy further or maybe completely vanish. In the next few million years, when the star becomes a white dwarf, they might no longer exist. It's also a testbed for extreme astrophysics. You didn't know they had extreme astrophysics, did you? Well, neither did I. So it's a testbed for extreme astrophysics. If confirmed, they'd be the closest analogs we have to disintegrating planets, like K1c 12557548. Call you later. The difference, instead of trailing dusty tails, these are stripped to their iron skeletons. Now, I know you're asking yourself the question, could life exist on here? And the answer is unequivocally, heck no. No, life is not happening on this planet in particular. I mean, these are hellish temperatures, no atmosphere, and a volatile orbit that would destroy anything organic. But they are the ultimate stress test for planetary models. I mean, they whisper. Doesn't matter how much gas you're born with, if fate or your star's expansion tosses you into a fire, what's left is really all that matters. Plus, because their existence is contentious, studying Kepler 70 BC reminds us of how delicate our detection methods are. Are these real planets or illusions born by stellar quirks? Next up, from blazing hellfires to the fluffy puffy. You'll get it when we talk about it. Welcome to the fluffiest corner of the exoplanet weirdness. And these are things that I never thought that I would say about space, but meet Kepler 51b, 51c, and 51d. These are gas giants that are so low in density, they're practically cosmic balloons. So think of Saturn, but lighter than cotton candy? Sure. So these planets are epic anomalies. I mean, roughly Saturn size, somewhere between 6 to 9 Earth radii? Whatever the plural of that is. But only a few Earth masses each, and the density is tiny. They're so puffy they'd float on water if you could find a bathtub big enough to hold a planet. Go figure. So how did these cosmic marshmallows form? And remain intact for that matter? I guess it starts when they were just kids. Kepler 51 is a mere 0.5 billion years old compared to our 4.6 billion year old sun. These planets likely formed outside the snow line, where ice are plentiful. Then they migrate inward, dragging a fluffy hydrogen-helium envelope with them. But close in proximity to the star means that their envelope should have evaporated fast. So why are they still intact? Well, that's where the real mystery begins, is high-altitude hazes. So you're thinking of photochemical particles lift light vapors above the atmosphere, making them appear larger, like a fuzzy halo. So recent JWST, the James Webb Space Telescope, and Hubble spectra of 51b and 51d came up featureless. So there was no water or methane signatures supporting the high-altitude haze/ring hypothesis. So this system is more than puffy, it's a cosmic symphony. The 3 known planets are locked in near resonance orbits, and the James Webb Telescope even caught Kepler 51d's orbit 2 hours early, suggesting another planet is also tugging on it. So voila, Kepler 51e was identified via these gravitational whispers that occurred around planet 51d. So this really confirmed that even bizarre systems are even more complex than suspected. So one more twist. The JWST has constrained Kepler 51d's rotation, slow and spherical. If it had spun fast, then centrifugal force would make it noticeably oblate. Instead, its rotation takes at least 33 hours, which is surprisingly sluggish for a planet so young. So maybe it formed with a little angular momentum, or something is breaking it? So in all actuality, why should you care? So, planet formation theory. Super puffs challenge our models. How do they hold on to atmosphere despite stellar assaults? Then you got exoplanet demographics. There are probably more puffs hiding in Kepler and TESS data and radar for the future. And then JWST revelations. Upcoming observations at longer IR wavelengths may see through the haze and finally let us measure the fluff. And then there's the laboratory for evolution. These planets will shed atmosphere over millions of years, so it's a good time to, watch and learn. They show us that young planetary systems can look utterly weird, and what we observe now might not survive long term. They're fleeting, they're fragile, and they're scientific gold, honestly. From marshmallow planets to orbital ghosts, Kepler delivers weirdness in spades. So our next stop is Kepler 7b, the first exo-cloud mapper. All right, cloud chasers and weather-weary Earthlings, next on our cosmic tour, Kepler 7b. It's as hot as Jupiter, it's extraordinary, and the first exoplanet to have its clouds mapped. Yeah, that's right. Way back in 2013, scientists painted a weather forecast for a planet 1,000 light years away. Think of a hot Jupiter. It orbits its star every 4.9 Earth days at a blistering pace. Can you imagine how fast that is? Surface temperatures of about 1,540 Kelvin, and that's like standing next to lava on steroids. But unlike other hot Jupiters, Kepler 7b is unusually reflective. It has this geometric albedo of about 0.35 to 0.5, and that means it reflects 35 to 50% of incoming starlight. Like a cosmic disco ball, if you will. Most hot giants absorb light, so this planet is really raising some eyebrows on the fact that it's reflecting it. So here's the magical bit. Kepler tracked brightness changes across 3 years, and Spitzer tipped the scales by measuring the infrared thermal glow, or lack thereof, combining them, and voila! By analyzing visible and infrared phase curves, scientists deduced the bright side wasn't heat. It was clouds. So they saw bright reflections peaking not at noon, but slightly in the evening hemisphere. It's a signature of a patchy cloud drifting westward. For the first time, they could draw a low-resolution cloud map for an alien world. And these clouds were likely made of silicate minerals, tiny droplets of molten rock. So this wasn't just cloud gazing either. It was a milestone. It was the first cloud map beyond our solar system. It proved phase curve analysis is a viable weather tool for exoplanets, and it also opened pathways to study cloud chemistry, the atmosphere circulation and climate stability on alien worlds. It also served as proof of concept for future studies by JWST, aerial and next-gen missions targeting Earth-like planets. So the next time you complain about cloudy weather at home, just remember, you could be living on Kepler 7b where clouds are made of rock and storms don't come with an umbrella emoji option. So there's that. All right, Space Voyagers, we are now heading into the prime time territory. You ready? This one steals the show, and not just for the science, but for our collective imagination. I want you to meet Kepler 186f, the first Earth-sized planet ever discovered in the habitable zone of another star. So cue the applause and UFO emojis. So let's break down why Kepler 186f is the Kepler superstar. And we can start with the radius. It's barely bigger, but yet enough to be Earth-like. Its orbital period is around 130 days, and it's much closer than Earth, but around a dimmer sun. Now, the light it receives is about 32% of Earth's solar flux, so roughly 1/3 of our sunshine. And as far as the mass goes, not directly measured, but predicted to be 1.4 to 1.7 Earth masses, assuming an Earth-like density. Now, the temperature is 188 Kelvin, or it looks like -85 degrees Celsius, but with a greenhouse effect, it could warm above freezing. So it's not just bigger, it's the right size to maintain rock, plate tectonics, and a stable climate. Now, Kepler 186f sits in the Goldilocks zone, so it's not too hot, it's not too cold, but this cozy place comes with some caveats. One of those caveats being it orbits an M1 type red dwarf. So a star about half as massive as our sun and roughly 4 billion years old. Now, red dwarfs can be flare happy early on, blasting UV radiation that can strip atmospheres, especially tricky if the planet is tidally locked with no magnetic shielding. But many are calmer in later life, and models show an atmosphere with 0.5 to 5 bars of CO2 and nitrogen could keep surface temperatures above freezing, even near the outer habitable zone. So yeah, it's plausible that liquid water and Earth-like conditions could exist if the planet has managed to hold onto its atmosphere. Okay, and I guess next up is earthiness. Tidally locked? There is a 50% chance its side is permanently turned towards its star, but atmospheric modeling suggests that weather systems and winds could redistribute heat, thanks to the circulation. And then there's the axial tilt seasons. If any hidden planet lurks between 186e and 186f, or if there's a large moon, obliquity tilt could fluctuate by up to -20%, enough to give seasons, not just eternal day and night. And climate modeling, detailed 1D to 3D climate sims show that the right atmosphere, 186f could maintain liquid water. Models even suggest mild, snowy winters and spring-like summers. Sounds wonderful. Now, here's where the storytelling kind of meets the science fiction. Young red dwarfs can produce massive flares and coronal mass ejections. Yet, studies indicate CMEs may be less destructive than feared, and some red dwarfs calm down after about, 1.2 billion years. So if Kepler 186f spins slowly and is tidally locked, can it generate a geodynamo, basically a magnetic field? Possibly. If its core remains molten, even a slower spin can sustain a magnetic field strong enough to shield its atmosphere. Plus, cloud formations on the sunlit side could help buffer radiation and regulate temperatures, so it's a double win. So between magnetic armor and atmospheric cushioning, Kepler 186f might just survive stellar chaos, with the emphasis on might. Kepler 186f trends harder than pop culture because it's where science meets hope. It's Earth-sized, in the habitable zone, potentially Earth-like. This is exoplanet fame. It launched a wave of curiosity and memes and novels and games and even rival Earth twin candidates like TOI 7000E and others from TESS. But it's 580 light years away, so way too far for JWST to do any type of atmospheric studies right now. But future telescopes like Lever, don't know how to say words today, or HABEX or ground-based ELTs might get some spectra data and maybe even detect biosignatures. So there's a real story here. A planet discovered, wonder, modeled, future hope. It's emotional, it's scientific, and it's cinematic. And that's the last planet that I have. I love the idea that Kepler found so many, and we're still studying some of the data that's probably still there. And when technology gets to a point where it can actually give us more information and a better outlook on some of our futures, I am excited to be part of that. So thank you for taking this journey with me. And if you haven't already done so and you enjoyed the content, please subscribe for any type of future stuff that I'll be creating. Thank you again. Archive out.